Welcome back all of you. Till last lecture we have discussed about stresses, and in today's lecture we will see a bit about strain in soils. And when I say we have discussed about stresses, I would like to make a disclaimer here, like whatever we have discussed is just a tip of the iceberg. Like this is only for orienting the listener or the participant of this course towards the higher realms of continuum mechanics. So, whatever we have learned, it is a very elementary discussion related to stresses, because in this course advanced soil mechanics we cannot go further beyond, because we have many other steps closely related to soils which need to be discussed. Now, in that whatever we have discussed about stresses, it holds true for the strain in soils as well. So, as you can see, much of the concepts discussed for stress is applicable for strain in soils as well. Now, when we discuss about stress and strain, one would wonder which is happening first and which is the manifestation of the other. What we know is that we have a body on which a set of forces or a force act. Now, this application of the force can bring about some changes in the body. Now, this changes one can visualize as the strain that is happening within the body. Now, when such changes happen, what is the internal response of the body, that we defined in terms of stress. So, both are manifestation of the load acting on the body, where you can always visualize strain that is happening in the body, and it is more like it is a reality, whereas stress is the internal manifestation. You may not be visualizing stress, but it is there in the form of response of the body. So, that is how we need to conceive this whole aspect. Now, deformable body subjected to forces. Now, forces, it can be body force and surface traction. We have not categorized these forces in our earlier discussion, and it was not required also. Only when we discussed about equilibrium equations, we mentioned about body forces, which becomes very important in soils. So, geostatic stress or the self weight stress becomes very important in soil and rocks. So, deformable body subjected to forces, it can be either body force or traction force, it undergoes rigid body motion and deformation. So, the two responses are rigid body motion and deformation. Now, when we say rigid body motion, it includes translation and rotation. We will not get into the details of rigid body motion right away. We will discuss at length about the deformation part of the deformable body. Now, deformation in general, it refers to change in shape and size. Now, possibly you will understand the implication when I say shape and size, because we have already discussed this in the previous lectures. Size, basically it relates to volumetric response, and shape, it basically represents the deformation or the shearing aspect of the material. So, when I say change in size, it is a volumetric response, and it is decoupled. So, we study an object which undergoes volume change, where change in shape is not discussed, that is the volumetric part of it, and the other one is deviatoric part, which we discussed earlier. So, deformation in general, it refers to both in general, but for soil mechanics or for rocks, the deformation which is associated with change in shape or shearing becomes very important. Now, strain displacement relationship, which ensures the compatibility requirements in the body. Initially, we discussed about stress and we have seen the equilibrium stress equation. That is one part of the story. The other part is strain displacement relationship, which will help to ensure the compatibility. All these elements are very much important for the study of continuum mechanics. Now, let us say that this is the given material. A compatible material, when it is subjected to different forces, is in this manner. So, this it is not failing as such, but it undergoes deformation. Hence, for the given situation we can call it is compatible. In this you can see that certain fractures are being made under the given condition of external forces. Now, this can be termed as non-compatible. So, strain displacement relationship helps to assess the compatibility requirements of a material when it is subjected to different loading. Now, compatibility is defined using strain displacement relationship. Now, we can say that U, V, W, these are displacement of a point in x, y, z direction. Okay. So, U, V, W, for example, if I have a body like this and I am discussing about this point may undergo, it is a microscopic phenomena, I am just enlarging it and showing you. So, this change, this displacement, if this is in x direction, then this corresponds to u. Okay. So, that is what it means. So, u, v, w are the displacement of a point in x, y, z directions, and infinitesimal displacement of a point. This is the actual displacement, and infinitesimal displacement of a point is defined by some continuous functions, and infinitesimal displacement in x, y, z direction is given by dou u, dou v and dou w. Now, let us consider this given axis x, y and z, and this is a given part of the body. First, let us define what is linear strain components. Now, as I told in the beginning, whatever we have discussed for stresses are applicable here. So, I am introducing the term strain tensor, and you need to understand it is one and the same, or it is very similar to stress tensor. Now, for that, in the stress tensor we had normal as well as shear components. Same way in the strain tensor also we have normal components that we discuss in terms of linear strain. So, linear strain components. Linear strain components, to define that, first let us see, this is the point A on the body and displaces by around dou u. Dou u is the infinitesimal displacement in x direction. So, dou u is represented, A is displaced to A dash. So, that is what it means. So, epsilon x, which is the linear strain in x direction, is given by dou u by dou x, dou u by dou x. Now, this is same as that of the definition of strain. So, similarly, we will have epsilon y is equal to dou v by dou y, and epsilon z is equal to dou w by dou z. So, these are called normal strains or linear strain. Okay. So, this is dou u by dou x, dou u is the infinitesimal strain, this displacement happening in the x direction, and dimension is given by dou x. So, epsilon x, epsilon y, epsilon z. So, these are called normal strains. Now, next we will move on to the shear components of the strain tensor. Now, again I will refer to x and z axis. Initially there was a body, and due to some sort of deformation, due to some response, what happens is there is a kind of deformation that is happening for the point C dash, which is given as dou u. Similarly, there is a deformation happening in terms of dou w here, and A and C points gets moderately shifted to A dash and C dash. So, there is a kind of shear happening on this body. So, here dou u is the kind of displacement that is happening in the x direction, and dou w is the displacement that is happening in the z direction. All those things remain same. Now, here it is all about deformation, and hence the rotational aspect of this becomes relevant here. Now, this is in dou z, this is dou x. So, we will first discuss about pure shear strain, or it is called tensorial shear strain. So, what are those? Now, the pure shear strain epsilon xz, that is in xz plane, dou u by dou z. So, what is epsilon xz? Epsilon xz is dou u by dou z. So, this is nothing but this particular angle. So, dou u by dou z is given as epsilon xz. So, what will be then epsilon zx, which is dou w by dou x. So, these are known as pure shear strain or tensorial shear strain. Now, there is another definition of shear strain which is known as engineering shear strain, where engineering shear strain gamma xz is equal to epsilon xz plus epsilon zx. So, this is the representation of sum total of the deformation that happens to the body. For example, if I rotate this about this point, one can get something like this. So, this becomes gamma xz. So, it is the sum total rotation that is happening is represented by engineering shear strain, and that is the sum of epsilon xz and epsilon zx. Now, we can take epsilon xz equal to epsilon zx. In that case, gamma xz is equal to 2 times epsilon xz. So, one can write the tensorial shear strain is half of engineering shear strain. So, in the tensorial form, it is represented either in terms of epsilon or in terms of gamma, whatever be. Hence, we can write now epsilon xz equal to epsilon zx is equal to half of gamma xz. What is gamma xz? Gamma xz is equal to epsilon xz plus epsilon zx. Now, what is epsilon xz? That is equal to dou u by dou z, which is written here, and the other one is dou w by dou x, which is written here. So, that is equal to half of gamma xz. It is very clear from this expression. Similarly, we have epsilon xy equal to epsilon yx is equal to half of dou u by dou y plus dou v by dou x. And then we have epsilon yz is equal to epsilon zy is equal to half of dou v by dou z plus dou w by dou y. So, what we have done? We have discussed about the normal strain as well as shear strain components. So, there are 6 strains which are functions of 3 displacement. Which are the 6 strains? 3 normal and 3 shear strain components, and they are function of 3 displacements, and hence they are not independent. For compatible displacement to exist, now what is the whole idea? When some force act on a body, whether it is under stress equilibrium, whether it is compatible, these are some of the questions one need to answer. So, for compatible displacement to exist, all components of strain and its derivative should exist, which means it should be bounded. It should be continuous to at least second order. Now, these are certain mathematical requirements to understand whether a given system is compatible or not. The displacement field must satisfy any specified displacement or restraints imposed at the boundary, that is satisfying the boundary condition. So, all components of strain and its derivatives should exist, again the mathematical requirement for continuity, and it should be continuous to at least second order, and displacement field, it should satisfy some specified boundary condition. Now, for elastic continuity, following conditions should satisfy, that is displacement continuity, the way in which we define u. slope gradient continuity. The slope gradient continuity, which is given as dou u by dou x, and the curvature continuity, which is the higher order derivatives dou square u by dou x square, should exist. Similarly, the other partial derivatives also should exist. Now, having done that, it is quite easy now for you to visualize. Since you have done with stress tensor, it is very easy for you to visualize strain tensor as well. We do not have to discuss more. So, this is the representation of strain tensor, epsilon x, epsilon y, epsilon z. These are linear strains or normal strain components, and other components epsilon x y, x z, these are shear strain components of strain tensor. And to expand this, you can see that it is expressed in terms of pure shear strain or tensorial shear strain, and hence we have half of engineering shear strain, which is expressed here. I will not go into the details, it is self explanatory. Just like we had stress invariance, it is true for strain also, it has strain invariance, but again I will not go into the details of it. And a very prominent strain invariant is the volumetric strain epsilon v, which is the sum of the linear strains, or epsilon x plus epsilon y plus epsilon z, and in principal strain it is epsilon 1 plus epsilon 2 plus epsilon 3. Again, deviatoric strain, as we have seen previously, there are different ways by which deviatoric strain or stresses are discussed or it is defined. So, same way deviatoric strain is also defined, and one such definition is, which is equal to root 2 by 3, which is root of epsilon 1 minus epsilon 2 square plus epsilon 2 minus epsilon 3 square plus epsilon 3 minus epsilon 1 square. It is similar to whatever deviatoric stress that we have discussed before. Now, deviatoric means we understand that it is going to create some sort of shearing component and deformation, the associated deformation. So, again octahedral stress we have defined here, octahedral strain gamma octahedral is equal to 2 by 3 root of epsilon 1 minus epsilon 2 square, it is the same inside the root. So, to summarize the strain acting in the soil, similar to stresses, there are 3 normal strains and 6 shear strains that form a strain tensor. It can be expressed as linear strain, or it is a tensorial strain, engineering shear strain. So, one is normal component and the other one is shear component of strain, which is tensorial shear strain, or it is known as engineering shear strain. The rule of transformation of coordinate axis we have discussed for stresses, strain invariance, principal strains, volumetric strain, deviatoric strain, all are valid for strain tensor as well. So, this is all about strain acting in the soil with relevant to this particular course, and there are lot more which you will study when you do a course in continuum mechanics or in geomechanics. Okay? So, this is all for now in this particular course related to strain in soils. Now, why we have discussed about stress? We have discussed about stress, we have discussed about strain. Now, where are we leading to? We are leading to what is known as cause effect relationship, which we will see in the next lecture. Thank you.